All right, this video is just going to be a giant video of examples. There's so many examples. There's 3 pages of examples that we're going to do together. And then there's extra examples that's not going to be graded, even though it says it will. There's extra examples at the bottom that you can also work on and ask me if you have questions about, and we can talk about those together as well. Let's start with linear regression number 1, some examples. Match the correlation. So remember, correlation, negative, means negative slope. Okay. Negative R value is negative slope. Positive R is positive slope. If it's close to +1 or -1, is strong. Otherwise, it's weak or on the weaker side. So let's just kind of look at these. Let's look at this first one. Let's look at this picture. What do we think R should look like for this picture? Well, it's not linearly related, right? There is correlation here, but it's like a parabolic or a quadratic correlation. It's not linearly correlated at all. We should have very weak correlation here. Letter C. Weak correlation is a number close to 0. All right, basically, there's no linear correlation, right? 0 would be no linear correlation. So C of 0.06 is very, very small. 2, this is positive and fairly strong. So I can't write the word strong. Look at our options, A, B, C, D. What's positive and mostly strong? D. Here, this is positive, but this is pretty weak. What's positive and pretty weak? B, 0.45. This last one is negative and maybe moderate to weak. That's going to be negative 0.7. Letter A. So that's how you can kind of approach these. Look at the picture, think about what we expect R to be, and then look at our choices to see which one's the best choice. Next scatter plot is going to show the relationship between the number of rebounds in a season. It's going to be our X, our independent or explanatory variable, and free throw percentage, the rebounds and free throws. It's going to be Y, our response variable, our dependent variable in the NBA, for players in the NBA. So what can we say about a player represented in the top left of the scatter plot? What can we say about a player in this region? Well, that's somebody who doesn't get a lot of rebounds, but does have good free throws. So in the, what is this thing over here? I don't want that. Top left. That's going to be a player does not get a lot of rebounds, but has a high free throw percentage. And again, bottom right, going to be the inverse, right? Player has a lot of rebounds. I don't know the English. I don't know anything about basketball. But a low free throw percentage. And I'm sure if you knew more about basketball, these correlations might make sense. Does the direction of association appear to be positive or negative? Well, if I had to draw a line here, I'd maybe draw the line kind of something like that. Or maybe a little flatter. So there's negative correlation, right? The slope is negative. We're going to say negative. Explain what the direction of association means in this context. That the more rebounds the player has, the lower their free throw percentage tends to be. And of course, this doesn't mean that if I have a really good game and I get a lot of rebounds, that my free throws are going to be crap, right? Just there's a correlation between players with these data points. And again, if I knew more about basketball, I'm sure I could describe why that is, why there's that correlation. Maybe you do. If so, tell me. I'd be curious. So which value is the best guess at the correlation? Specifically, which one of these do we think our R is going to be? So right off the bat, let's approach things in steps. Why can these ones not be R? Our correlation coefficient. Remember that our correlation coefficient is always between -1 and 1. So it can't be a number outside of this region. And specifically, I'm going to change to green. I know the correlation coefficient is not -1 or +1. Because if it's equal to +1 or -1 at the very end, that's perfect correlation. It means the data points all lie on a line. I can get rid of some more ones too, right? 0 is when there's no correlation. Oh, that's hard to read. 0 is no correlation. Don't use yellow. Don't use yellow for that. Oh, I can still use black. Is our correlation positive or negative? We said it's negative. Well, if correlation's negative, right, these would be positive correlation. We don't have that. There's only 2 options left. Strong or weak. Well, these data points are very spread out. I think this correlation's weak. So we're going to say that it's not 0.9 either, because this is only for strong. So our best guess out of these options is -0.4. That's how you can approach this. I color-coded all of the problems. These blue ones don't work because it needs to be between -1 and 1. The green ones don't work because these ones are perfect correlation. Black ones don't work. The black ones are positive. Yellow one, you can't read that anyway. It's not important. Just kidding. Yellow is 0, means there's no correlation or no linear correlation. Which of the values in part D are impossible? Oh, we already answered that. -20, -2, 2 and 20 cannot be correlation values. And -1 and +1 are realistically impossible, but theoretically possible. All right, next problem. Do you expect a positive or negative association between the 2 quantitative variables? Also, I didn't say this earlier, but it's a very good idea to pause this video right now. Do all of these. Do all of these on your own. And then check the video to make sure that you're correct, and check the video to see if you're confused, to figure out what the thought process is for all of these. Don't just watch this video like you'd watch a TV show. This video especially. Work on these problems first and then listen to me. Or maybe don't listen to me at all if you got everything right. All right, and I'm not even joking about that. In each case, do we expect positive or negative correlation between these 2 variables? Remember, positive means as x increases, y increases. Negative is as x increases, y decreases. So do they move in the same direction or opposite directions? Can't write. Number of years in education and annual salary. Does more education correlate to a higher salary for US adults? Or does more education correlate to a lower salary for US adults? If they both go in the same way, that's positive. Opposite ways is negative. Well, the higher your the more years in education you have on average, the more money you're going to make. There's a positive correlation here. How strong is it? I don't know. We'd have to look at some data. There's definitely positive correlation. Age and maximum running speed for adults, right? Because if we weren't looking at only adults, then yes, as you're growing up, your running speed would increase, then maybe kind of like plateau, and then as you get older, your running speed would decrease. But we're only looking at running speed for adults. There's negative correlation. And again, maybe it plateaus for a while or is pretty constant from like 20 to 40 or whatever, I don't know. But on average, it'll decrease. Age and maximum running speed for children. Oh, that was the other half of the graph, right? As a kid is getting older, we'd expect their running speed to go faster in general. Not all kids, but in general. There's a correlation there. They move in the same direction. Increase the X, increase the Y. That's positive correlation. They go in the same direction. Baseball games can last a long time. Every baseball game, almost every baseball game I've ever gone to in person, it's been so boring, nothing has happened, and it took forever. Anyway, my own personal feelings aside, how is the length of the game, measured in minutes, influenced by how many total runs there are? If there are 0 runs, you have 5,000 innings, but your personal feelings aside, Jason, it doesn't look like we're looking at any data point. Well, I guess you literally can't have 0 runs at the end of the game, right? Someone has to score eventually for the game to end. I don't remember how baseball works. Anyways, don't know basketball, don't know baseball. Hopefully these are applicable to some of you. How is the length of the game influenced by the number of total runs? A scatter plot with regression is shown below, and the regression line is given by time hat. Instead of y hat, we're using time hat here, is that equation. So we could write it with x's and y's, but they're using the variables with words. That's fine too. Use the regression line to predict the length of a game in which 5 runs are scored. 5 runs are scored. It's going to be right here. About 170 minutes, almost 3 hours. Let's get a better description. 5 runs are scored. Just plug that in right here. So time hat is going to be equal to 158 plus 2.53 times the number of runs. Type that into a calculator. 158 plus 2.53 times 5. Going to be 170.65, or about a little under 3 hours, about 171 minutes. Remember that our time variable is given in minutes. Too long for me. Maybe it's great. Maybe you like 3-hour baseball games. So there's one game. In one game, 5 runs were scored and the total time was 189 minutes. So in one situation, we're looking at this data point right here. Find the residual for this blue data point, 5, 189. Well, that residual, remember the residual is just the distance between the line and the data point. We also had a formula. You could look at the formula. It's earlier in the notes. Not residential. Residual was the outcome minus the prediction, or the point minus the location on the line. Well, the actual one was 189 minutes minus the prediction. We have to figure that out. Prediction was going to be 158 plus 2.53 times the prediction. Oh, we calculated the prediction in part A. Prediction was about 171 minutes. So type this into a calculator and you're going to get about 18 minutes. For that residual. You get more decimal places if you wanted. It'd be like 1835. So for this same game, circle the corresponding, oh, well, circle it. We already showed it on the graph. There we go, we've circled it. Interpret the slope. First off, we need the units, and then we need an explanation. Remember, the slope has to do with, this is the increase in y if we increase x by 1. And the units are always the units of y divided by the units of x. Units of y is minute divided by the units of x. How many runs? So this is our slope. So on average, increase x by 1, increase the number of runs by 1, you get 2.5 extra minutes of this ball game. Okay. On average, takes 2.5 minutes more for every additional run. That's how we interpret the slope. Interpret the intercept. What is the y-intercept? The y-intercept is 158. 158, Jason? Minutes? Y-intercept is a y value, so the units are going to be the units of y. And this says the y-intercept, again, another way of thinking about that is x equaling 0. If there are no runs, it takes about 158 minutes. But again, I'm pretty sure someone has to score at least once for the thing to be over. So this is, I think, if I read more about baseball, this is not possible. But a game would take about 158 minutes, even if there were no runs. Or again, if that's an impossible situation in baseball, you could say 158 minutes is the baseline for game length. And it takes 2.5 minutes for every additional run. Another way of combining everything all together. All right, last page of these examples, and then you can do the stuff after this on your own and ask me if you have questions or want to check your work. This is the last one we'll do all together. CarMax.com is listing numerous Toyota Corollas for sale within 250 miles of Redlands, California. And we have the ages of all of these Toyota Corollas and their advertised prices. Make a scatter plot. GeoGebra and so here we're going to try something. If I just paste this into GeoGebra directly, it may or may not work. Probably won't if I paste it directly. That's fine. But what I want to try to do, I want to try this tip that somebody else shared with me of trying to paste it into Excel. Sometimes this works if you paste it into Excel. All right. It actually did not work. We'll just copy it down manually. Okay. Oh, my Excel is crashing right now. That's interesting. Well, no matter. Type this in manually. Whoa, there's a matter now. Thank you. You Windows. All right, it's all good. So 9, 4. No, I don't need you down there. Go away. 4, 7, 3, 5, 5, 8, 9, 1, 5, 3, 5, 8. Next to that, there's too many 9s in sales. All right. Ooh, almost had a bit of a problem here. 16998. All right, so we highlight this data, click up here to variable analysis. Yeah, if you don't have the regression line automatically, go down here and select linear. All right. And we can get some data about this regression line as well, dragging things where they need to be to make things look nice. So that's our scatter plot. We could save it by going up here. All right, so we've done the scatter plot. We've done that. Didn't ask us to paste it or anything. It just said to make it. Are there any outliers? Okay, yeah, it looks like there is one. Right, this thing over here is way off. Which data point is this? This is 8 and something that's like $17,000. So let's look at something that's around 8 with $17,000. This one at the very end. This guy is our outlier. And specifically, look, it says for future questions. So again, yes. 8-year-old Corolla for $16,998. So it says use the better model. It wants us to get rid of this data point. Okay. Data point's gone. Let's reselect and use this better model without that outlier. All right. Describe the association between age and price. Ages are X, prices are Y. As X increases, as we go to the right, what's happening to our Y values? As we go to the right, these data points are getting smaller. And there's a negative correlation. Negative linear correlation. Right? The older the car, the cheaper. Do I think a linear model is appropriate? Yeah. And again, you can kind of play with GeoGebra a little bit. We'd use a logarithmic model. It actually doesn't look too bad either. You could compare the sum of squared errors and the R values. You use a polynomial model. Even our polynomial model is almost like a line. Power model, that one doesn't look so good. Exponential model, again, pretty close to a line. Sinusoidal model. Actually looks pretty close, but I don't think cars oscillate like this. You can play around with this. Logistic model, it doesn't even know what to do. But yeah, I think a linear model works pretty good. Yeah. Compute the coefficient of determination and explain the meaning. So remember, that's asking coefficient of determination, that's R squared. R is negative 0.8658. And this tells us the strength and the direction. Tells us it's negative correlation with an inverse relationship. And it's close to -1, which means it's strong correlation. But R squared, that's the coefficient of determination, and that meant something different. So if we square this value, so negative 8658, and we square that, it does become positive, it always will. R squared is about 74.96%. Again, R squared is usually written as a percent. So we could say about 75% of the data, about 75% of the variation in Y, the variation in prices are Y, can be explained by a variation in age. Okay, so about 75% of that difference can be explained by age. And 25% of the variation from our model cannot be explained by age and would have to be explained in some other way. Equation of the regression line, y hat. GeoGebra gives it to us directly. Down here, -844. Makes sense to kind of round to the nearest dollar here. I'm going to give more digits just to be safe. 4639. X plus 17,673. 0.965. Again, explain the meaning and the y-intercept, or meaning of the slope and the y-intercept. That slope is that -84,844.4639. What are the units of slope? They're the units of y, price, divided by the units of x. This is going to be -$844 divided by the units of x per year. And again, the y-intercept is the units of y, 17,674 about. So what we're going to say, right, is on average, as we increase x by 1, increasing x by 1 is having things be a year older, the price drops by $844. The price decreases by about $844 for every year a car gets older, or for every year these Corollas get older. Since these Corollas, Toyota Corollas, have been made. English is hard. And I'm talking too much about cars and sports today too. And then we could do something very similar for the y-intercept. Y-intercept is when x is equal to 0. So the cost of a new Toyota Corolla is about $17,674, given this data. I don't know when this data was recorded. I don't know the cost of new Toyota Corollas either, but that's what the model is saying. So if you want to sell a 7-year-old Corolla, what price seems appropriate, given that you're close to Redlands, California, in this time period, whenever this is? Well, we could just use an approximation. The y hat is going to equal -844.4639 times x, which is 7, plus 17,673.965. And say, all right, an average, a good decent price for a 7-year-old Corolla is what happens when you type this into a calculator. Say about $11,000, 763. Let's double check. Does this make sense? For a 7-year-old Corolla, a little less than 12,000, given the data. 7 years old is right here. A little less than 12,000, sure. There was a 7-year-old that was going for a little less than that, but our estimate is on this line. Our estimates are always going to be on the line because that's how we find the estimates. You see a for sale sign on a 10-year-old Corolla with an asking price of $8,500. What's the residual? Well, 10-year-old, all right, it's outside of our data set. Outside of our data set, we're extrapolating now. Kind of hard to talk about. Okay, this is outside of our data set. Our model is less useful. But it's still kind of close. We can use it a little bit. Our prediction here, just change the 7 in the last example to 10 and see what our prediction should be. Our prediction is that it's 92.29. So yeah, maybe it's a good deal. Hard to say. It's hard to predict. So I'll say maybe. consult more resources. I think the question is probably asking for a yes, but again, we are outside of our data set, so we're a little bit in uncharted waters. If I had to choose, say yes, probably. But for a 25-year-old car, no, this is way too far out. All right, this is way too far outside of our data set. So no. Okay. Again, there's some more problems. There's no points. There's more problems if you want to work on them and ask me questions about. I'd love to use this as a springboard to talk about more regression stuff, but you don't have to. So they're there if you want them. Otherwise, you don't have to. So email me or message me if you have any questions, and have a great day.